Hello everyone, welcome to Stochastic Calculus for Finance 1. This is the continuation of section 4.4 on the general American derivative. So in the previous video, we went through definition 4.4.1, which went basically over the definition of the price process followed by an American derivative security. And the stochastic process followed by the price of an American derivative security is given by this expression here that we went through over our previous video. And now we will go over theorem 4.4.2, which goes through the properties of the American derivative price process. So the first property says that Vn, at any point in time, essentially at any point in time, the price of the American derivative security is greater than 0, and that makes sense because the price of an American derivative security cannot be less than 0. And Gn, which is basically the intrinsic value of the option, how much money do we get if we exercise the option today? The price of the derivative security has to be greater than this amount here. Then the second property says that basically, if we take the discounted price process, it is actually a super martingale. And finally, if we take any other process yn that satisfies basically property 1, that yn is greater than the intrinsic value and is greater than 0, and that the discounted price process is also a super martingale, then this process yn has to be greater than Vn. So essentially what this is saying is that Vn is the smallest process really that satisfies 1 and 2, where 1 says basically the process is greater than the intrinsic value and 0. So this is saying us basically this Vn is really like the tightest process on really the price of this American derivative security. Now to really understand better these properties, we'll go and prove them one by one. So to help with our proof, I put here basically the definition of the American derivative price process, which is given here, and this is the property. It is the theorem 4.42 with all the three properties that we want to demonstrate. We want to show. So first we need to show property 1. So we can let theta hat be in delta in the set Sn, the set of all the stopping times. That takes value of, but this one actually takes the value of n no matter what the coin toss is. So the theta hat is just like one special case, one special stopping time inside this set here, right? So because theta n always take the value of n, then basically we just need to replace theta hat here by the value n, right? And when we do that, we find essentially Gn, and that's very simple to see. I'm not sure if I should show this, but let me just show this very quickly. So essentially, this is just E. This is just equal to the expected value as we stand of time n of the indicator of function of essentially here, since theta hat is always equal to n, this is n less than equal to a capital N, and this is true. So this just like basically boils down to 1, and 1 divided by 1 plus r. Theta hat is just n minus n, right? And this is just here times j theta hat, which is just n. So if you look, this also just boils down to 1. This is jn, and since like we at time n, we can take out what is now, and this is gn. I don't know why I always call j, but you know what I mean. So that's this first part. So then we can show also, like we can pick also another special case of a stopping time that takes the value of plus infinity no matter what the coin toss is. So this is basically a stopping time where we say we're never going to exercise the option. So if I'm never going to exercise the option, then essentially the value here is just 0, right? Because this theta hat is actually plus infinity, so this thing is always going to be 0, and 0 multiplied by whatever is 0. So essentially what we just shown here is that, and if you remember, Vn is basically the maximum among all the set of stopping time. and we have shown that basically that Vn, we have shown that basically if we take theta hat, then we have Gn. If we take a special theta tau bar, we get 0. So that means Vn is basically essentially bigger than Gn, and Vn is also bigger than 0, right? Because these are just special cases of stopping time that are inside here. So hence Vn is greater than or equal to the maximum of Gn 0. And I think that this definition was probably kind of straightforward. Okay, so now let's look at property 2, which is saying that basically the discounted price process is a super martingale. So first we can take theta, we consider theta as tau star, which is in this set, and be the optimal stopping time in the definition of Vn plus 1. Okay, so essentially what that means, if you want to find the value of Vn plus 1, we can forget about the max, right? We can forget about this max here. We say that the tau star is basically the amount that maximizes the value of our option in this case. That's why basically we don't have the max, and we just put tau star here, and this is going to be basically the value of our option at time n plus 1. So now we know that basically tau star is included inside this since tau star is included inside this set, like we said earlier, then tau star is also included in this set here, right? Which makes sense because delta n is actually a bigger set than this delta n plus 1, right? Because this one contains the set of all stopping time that can take value from n to the end of our period, or maybe we can never exercise. And this one contains the set of all the stopping time that can take value between n plus 1 or the end of our period, infinity, right? So of course this set here is bigger than this set here, so this set here is bigger than this set here. So tau star is also included in this. Hence we can say basically Vn is greater than this relationship where we're using tau star, right? And the reason is because Vn is the maximum over like this bigger set, and this set delta n actually includes this tau star is actually included in this set. So this relationship hold. And when we know this, then we can use essentially iterated conditioning, right? So if you notice, we can take, yes, as we have seen this in section 2, in chapter 2, I believe, that we can use iterated conditioning. So if I take the expected value as a time n, that's the same thing as basically taking the expected value out of time n1, and this is just like iterated conditioning, where like this value here is exactly the same value that we're seeing here. Now with this, from here we can take one plus r to out, right? So we take it out here, and since we took like this factor out, that's where this -1 is going to come from. Okay, and now if you pay attention, you should see that basically this thing here looks strangely like this relationship what we're seeing here, right? And actually it is exactly the same relation. So we can essentially replace everything here by Vn plus 1, and which is still makes a lot of sense. So then if we divide both sides by essentially 1 plus r to the power n, we get basically this expectation as return of time n, Vn plus 1 the next time period, discounted by 1 plus r to n plus 1. So essentially what we have shown basically is that this process is a super martingale. So we had the random variable that we showed that at time n is greater than equal to the expected value as return of time n of this random variable at time n plus 1, right? So as time passes by, we expect essentially the stochastic process to continue in the future and kind of like decrease, and that's basically the definition of a super martingale. So we have just shown basically the property 2 holds. Now let's show property 3. Let's prove property 3. So let's delta n yn to be another process that satisfies property 1, and property 2, and we let this to be a stopping time inside this set. Then we'll have this property is actually holding. So to think about this, we can really think about two cases. We can think essentially that so let me write this down very quickly. So to is inside this set, right? So that means to can take values that are in the set n plus 1 up to capital N, right, at the end of our period. Or maybe we never exercise the option. But obviously, for example, okay, so let's imagine we never exercise the option, right? So that means like this to is equal to plus infinity. If to is equal to plus infinity, we have seen that basically that Vn is if I have American derivative that I never exercise this American, then that means like the value this value of this American is going to be 0, right? If I never ever exercise it, and this Yn then is always going to be greater than or equal to 0. So essentially, like if we decide we're never exercising the option, so the properties already holds, right? Okay, so now that means we can just consider the cases where like maybe we're exercising the option sometime. Maybe we can exercise the option today, maybe we want to exercise the option tomorrow, or maybe exercise the option like expiration. So in this case, then this thing is going to hold because this to is exactly equal to essentially the minimum between this to and n, the time period, right? Because if you take the minimum between to and n, this is simply to, because we imagine to is in this set here. So that makes sense. So here we haven't done anything fancy yet. And this is actually equal to less than or equal to this amount here. And what has changed now is basically this jt has been replaced by this y2. And this also is very easy to see why, because we're saying essentially that this y, the stochastic process is satisfying property 1. And property 1 is saying essentially that Yn is greater than or equal to max Jn 0 for all n that we can think of, right? So that means this is true for n if n equal to 2 also, right? Y2 is greater than or equal to the max of this J2 0, right? And so that means like essentially Y2 is greater than or equal to it. It's fairly straightforward. So that's why like this inequality here is coming from. And the next step, since we're saying like again that to is between n, small n to capital N, then that means that we can just add this thing here. We're not changing anything, right? That's exactly the same thing. And now if you remember well, we're saying like basically this stochastic process y satisfies property 2, right? And property 2 is saying the discounted process is a super martingale. So all that means is essentially that this expectation here at the next time period, at some other time period in the future, is going to be essentially less than or equal to the random variable at the period today, right? So today with at time n, so it's going to be less than this amount here, which again is just like the property of the super martingale that we're being used here, and we're exploiting the fact that Yn is satisfying property 2. And this is the same thing essentially, right? Because to can be equal to n up to capital N, right? So if I take again the minimum of this to n, obviously it's going to be just this n, and that's all we did here. So we can take this and multiply both sides by this, by 1 plus r. So if you multiply by 1 plus r, I get basically this Yn here. And if I take this and multiply by 1 plus r, multiplying by 1 plus r to the power n is the same thing as multiplying by 1 plus r to the power minus n. So that's where this minus m is coming at the denominator here. And now if you pay attention, basically this thing here looks very similar as the definition here, right? These two looks very similar, but for Vn is actually the maximum among all the tau star that we can, among all the taus that are inside the set delta n. But we're saying this relationship hold here for any tau that's inside this thing here, right? That's the definition we have. Let tau be a stopping time in delta n. So this tau can be any stopping time really. So of course this tau, so no matter what tau I take inside this set, is going to be less than yn, right? So that means basically if I look at the maximum over all the taus that are in this delta, this set delta here, is going to be also less than yn. And that's so that means basically Vn is less than or equal to yn. And this is the property that we wanted to show. And this is the property actually that proves and that justifies that yn is a good price for this option. The option is not like something crazy like $1 billion. The option is not something really, the value of the option is something reasonable. That's kind of like, it's really the smallest price, the smallest process related that's that can make sure that we always respecting this relationship here. Okay, so that was property 3. So now just as a recap, I put here, we have seen the definition and we have seen basically property, we have seen the definition of the stochastic process and we have seen also the properties. So now we can go and really talk about very quickly about American pricing algorithm. And you probably guessed it, it's not too complicated. At maturity, the payoff of the auction is going to be either between 0, right? If I don't exercise the option, I get $0. Or if it makes sense to exercise, I get GN, right? Which is just the intrinsic value at maturity, the payoff. And at any time before that, essentially we use this American pricing algorithm, where we can use it recursively from the end to today. And basically the value of the option at any node, when we use the tree for example, is going to be equal to between the maximum of the intrinsic value. If I exercise the option today, how much do I get? And essentially the risk neutral pricing formula that we have seen before. And there's actually the proof that shows that basically if you do this, if you follow this algorithm, you'll find exactly the same process as this the definition we've shown Vn here, but I'm not going to prove that. I think we have seen this recursive pricing on the tree quite a few times, so it's probably not so critical to know. Okay, so here, like essentially the three things we have seen: the definition of the stochastic process, we have seen the properties of the stochastic process, and an algorithm to be able to build this pricing if we were building some trees. So this is essentially theorem 4.4.4, which talks about how can we replicate a path-dependent American derivative. And so it's very simple. Like as we have seen before, we're going to define the delta, right? So if we stand at the given node, the delta is just going to be equal to the value of the American derivative. If we flip the coin and we get a tail, I'm assuming we're still working in the binomial asset pricing model. And the value of the option if you get a tail, value of the option if you get a head, and the difference in the value of the stock price or the underlying as well. And there's this concept of consumption that can happen if the value of the option today is greater than basically the value of the risk neutral pricing. Assuming that we're not going to exercise the option today, then there's like certain amount Cn which we can consume and still be able to hedge this, right? So we're trying to replicate the American derivative by trading in the money market and the underlying. And this delta is essentially giving you how much you can of the underlying you should hold, and the Cn sometimes you might be able to consume something. So if you start at the point where the initial value of our portfolio is equal to the value of the option today, then we can take this initial wealth and basically build a portfolio this way. and we have seen this many times also. So we will have basically the value of our portfolio will always be equal to the value of the derivative security, and in particular the value of our portfolio is always going to be enough for us to cover us in case we exercise the agent exercise the option today. Okay, so that's pretty much, I think, most of the things I wanted to talk about here. So we can talk about very quickly also about optimal exercise. So what we have shown so far is the definition of the stochastic process, the properties. We have talked about American pricing algorithm to price this on the tree, and we have talked also about how can we hedge or replicate this American derivative security. But we haven't really talked about how can we find the optimal time to exercise these American derivative securities. And this is what theorem 4.4.5 is tackling now. So if you pick a stopping time, let's call this tau star, right, which is the minimum time, which is the minimum value n, such that the value of the option, the price of the option is equal to the intrinsic value, then this is actually basically the optimal stopping time to use. So the stopping time maximizes the right hand of definition 4.4. So we want to maximize this value here. We want to find the optimal exercise strategy really to maximize the value of our option. And we're saying here that optimal exercise strategy is the strategy where you decide to exercise the option as soon as the value of the option is equal to its intrinsic value. The first time that this happens, that the value of the option is equal to the intrinsic value, then you just exercise the option, and that will maximize. That's the optimal stopping time. So let's show how we can. Let's prove this actually. Why is this the optimal strategy to exercise the option? So essentially, like, since we're saying this is the maximize it. So if we assume that we stand at time 0, then basically the value of the option at time 0 is just equal to this expectation here, where we're using this optimal strategy and tau star. So that means like basically we're removing this max here, we're replacing n by 0 and using this tau star here to say that's the optimal strategy. Okay, let's prove this. So I'm putting here essentially some things that we need. So this is basically the definition of like the stochastic process followed by the American derivative security, and we have Vn here, which is essentially, this is coming from the American derivative algorithm, pricing algorithm, right? So at any point in time Vn, of course we need to make sure that the value of Vn is either greater than or is the maximum between the intrinsic value if we exercise the option today, or the value if we decide to exercise sometime in the sometimes in the future. And this is essentially the formula that's coming from the risk-neutral pricing formula. And what we're trying to prove is essentially this: that tau star, which is defined by the stopping time defined by this, is the optimal time to exercise. So the key to prove this is to note that the stopping process is actually a martingale under the risk-neutral rule. So how can we show this? If we show that this is a martingale, then we're pretty much done. Okay, let's show that. So this tau star can actually be either greater than n. That means like so far we have never seen a case where basically the value of the value of the option is equal to its intrinsic value. That hasn't happened yet. Maybe it will happen sometimes in the future, given that if you think we like extending, it will happen after time n, right? And there's also another case. Maybe if we take a time n, right? Maybe sometimes in the past, like we already hit this case where the value of the option is actually equal to its intrinsic value. So let's see in both cases, how can we show it's a martingale? So in this case, this process here, right? If we know that this tau star is greater than n, right? And this just means basically the minimum between n and tau star. Then that means like basically this, we can just replace the whole thing by simply by n. Again, here we can just replace simply by n, right? Okay. And since we're saying like this hasn't this is true, that means like we haven't hit a case yet where Vn is equal to Gn, right? So that means essentially the value of Vn has to be equal to this amount here, right? So that means we can replace this Vn essentially by the reasonable pricing formula. So we have this amount here, and this 1 plus this discount value here is just giving here. And we can replace essentially this by Vn plus 1. Again, this we know that this is true because we're saying like tau star is greater than n. So that means like as we tend at time n, the value of Vn is not equal to Gn. So that means it has to be equal to this discounted process here. So essentially, yeah, and then so 1 plus r to the power n multiplied by 1 plus r is just basically this n plus 1 here that we put inside the expectation, and this thing is just basically the expectation of Vn plus 1 as we tend at time n. And essentially we have shown that we have a martingale, right? Well, maybe we can put this tau star. So this tau star, we know this tau star is greater than n, right? So this tau star is going to be either this tau star is going to be equal to n plus 1, or it's going to be something greater than n plus 1, right? So we can replace this here. Okay, let me show this very quickly. So the minimum of n plus 1 tau star, right? This is the same thing as n plus 1, because if tau star is greater than n, that means tau star can be equal to n plus 1, it can be equal to n plus 2, up to capital N or plus infinity, right? So that means this tau star, then that means that this minimum here is true. I mean, the minimum value of this tau star can be is n plus 1. So the minimum of n plus 1 is just n plus 1. Nothing too deep here. So essentially we have shown that we have a martingale, right? So this is the random variable we started with, and this is essentially it's equal to the expectation at time n plus 1. Nothing has changed, so this is a martingale. So let's come to this case here where we say tau star is less than or equal to n, right? So that means like as we stand here, this tau star, this event has already happened. They will have seen already a case where like the value of the option is equal to the intrinsic value, right? So this process has already been stopped. This is already frozen, and it has been frozen at this time tau star, right? So we can replace like these things here by simply tau star. And since this process has already been frozen in the past before we even reach at time n, before we even reach today, so that means like essentially these things, this is a constant. This is never going to change, and that's the meaning of like a stopped process, right? So if I take the expectation, this is the same thing as taking the expectation as of time n of this tau star. This is just a constant, so it's frozen again. So because it's frozen, basically we know tau star is less than equal to n, so of course it's going to be less than equal to n plus 1, right? And if we take the minimum of tau star of n plus 1, this is just tau star. So that's why basically I can afford to put this and again like this means minimum, right? I think we remember that. So that means like this thing here is the same, is just equal to V tau star. And that means this tau star also we can replace it by this amount here. Let's reply here. And essentially what we have shown again is that this process here is a martingale, right? Because when we take the expectation as we stand at time n, right, it's just equal basically the same variable when we go to at time n plus 1. So whether tau star is greater than n or tau star is less than or equal to n, this is a martingale. Hence we have shown that this process is a martingale. Now how can we use the fact that this is a martingale to show that basically this tau star that we define here is the optimal stopping time? Well, if we want to find the price V0 is nothing but essentially this process where we replace n by 0, right? Nothing too deep about that, because tau star can never be basically less than 0, right? Either I exercise the option at time 0 or I exercise the option at time 1 or going to the future. Okay. And then essentially this is the same thing. So because this process is a martingale, right, that means like any time in the future is when I take the expectation, it's not going to change, right? So this is just like the property of martingale. So I take 0, the 0 become n, but I'm taking the expectation, so I don't, they're still equal. And if you, and then this part might seem a little bit confusing to people, but from this step, from here, we can go to this step very easily. How? Because we can use an indicator function here. So this tau star can be equal to n. It can be equal to n plus 1. Or okay, since like we're starting at time 0, that means like this tau star can be equal to 0. It can be equal to 1 up to the end of our period, or maybe we can never exercise, right? So if we say like we're exercising this between sometime between 0 and time n, right? That means essentially that like this n tau star, this minimum can actually be replaced by tau star, right? So that's how we get this tau star here and this tau star here. And we're saying also that v tau star is actually equal to it's equal to g tau star. And why are we saying that? Well, we're saying that because if this tau star happens somewhere in here, then by definition we're saying like this v is equal to or to the intrinsic value, right? That's why the tau star happens sometime between, right? So that means we can replace basically v tau star with j tau star, and that's what's happening here. But if on the other side, basically tau star is actually equal to this, right? So this whole value here is going to be 0. If we want this other case, this is going to be 1, right? But then we're saying like tau star is equal to plus infinity. So that means we're never going to exercise the option. So essentially like this whole second part also here is just going to be 0, right? So the second part is going to be 0 if we like in this case. And in this case, if the tau star is actually less than n, then we just get this amount here, right? So since this is always 0, we can just simplify it to this. And essentially, we have shown that v0 is equal to this amount here, to this thing here, right? So hence, essentially that this tau star is the one that's maximizing this maximize this expression. This tau star is the one that's maximizing this just by identification, right?